Have you ever just looked at a model of our solar system and thought, how does it all stay so neat? I mean, you've got these massive planets hurtling through space at thousands upon thousands of kilometers an hour. It really seems like it should be a recipe for a catastrophic cosmic pileup. And yet, for billions of years, it's all just this perfect, orderly dance. So how is that even possible? How does this crazy high-speed traffic avoid total, complete chaos? Well, it turns out the answer isn't just one thing. It's actually a series of clues left behind by physics and time itself. So, you know what? Let's play detective and solve the case of the cosmic ballet. Okay, so our investigation has to start with the biggest object in the neighborhood, right? The sun. Its gravity is absolutely immense, and it's constantly pulling everything toward it. So the first real mystery we have to solve is, why don't the planets just, fall straight in? To figure this one out, we can turn to Isaac Newton and his famous thought experiment. So imagine a cannon on a crazy tall mountain. If you fire it slowly, gravity just pulls the cannonball right down to the ground. No surprise there. Fire it faster, and yeah, it travels a lot further before it lands. But now, what if you fire it at the perfect speed? The cannonball is still falling, but its forward speed is so great that as it falls, the Earth curves away beneath it. It's constantly falling, but it's always missing. And that right there, that's orbit.
That's exactly what the planets are doing. They're in a perpetual state of falling toward the sun, but their incredible sideways speed, what physicists call tangential velocity, means they're always missing the target. They are locked in this perfect, delicate balance between gravity's relentless pull and their own forward momentum. So the key takeaway here is it's not about avoiding gravity at all, it's about balancing it with speed. Clue number 1 solved.
All right, so the planets won't crash into the sun. Check. But that still leaves 8 of them. Plus, who knows how many other objects flying around. So what stops them from smashing into each other? Well, this brings us to our second clue. And this one goes all the way back to the birth of our solar system. About 4.5 billion years ago, our solar system wasn't really a system at all. It was just this giant, messy, slowly spinning cloud of gas and dust. We call it the solar nebula. Now, as gravity started pulling this cloud inward, it began to spin faster and faster. Just think of an ice skater pulling their arms in to speed up their spin. It's the same principle. And this super fast spinning forced the cloud to flatten out into a disk, kind of like a chef spinning pizza dough.
And this flattening, it had some huge consequences. Because all the planets were born from this same spinning disk, they all inherited its properties. This means they all orbit on roughly the same flat plane, and they all travel in the same direction. What this does is effectively turn our solar system into a massive, multi-lane, one-way highway. You don't have any rogue planets driving against traffic, which, as you can imagine, dramatically reduces the chances of a head-on collision.
So we have orbits keeping planets from hitting the sun, and we have this flat, one-way system keeping them from running into each other. It all sounds pretty peaceful, right? Well, here's the twist. This peace is a lie. The serene order that we see today was actually forged in an era of unbelievable violence. See, in the early days of the solar system, there weren't just 8 planets. There were likely hundreds of tiny protoplanets, all swarming around, all competing for the same space and the same material. The solar system wasn't a peaceful highway back then. It was a billion-year-long demolition derby of cosmic proportions. And what's wild is that this history of chaos is literally baked into the official definition of a planet. To be a planet, a celestial body has to be massive enough to have cleared its neighborhood. Now, this isn't just about tidying up. It means a planet's gravity has to be so dominant that it has either collided with and absorbed its competition, or just gravitationally kicked them out of the way.
And this is the absolute crucial point for our third clue. The reason our solar system is so stable is because we're only seeing the winners. The planets we have today are the survivors of that cosmic battle royale. Any planet that had a chaotic, unstable orbit, it was either destroyed or ejected billions of years ago. So the order we see isn't some miracle, it's just what was left over after the chaos.
Okay, so the survivors have their own clear lanes. Makes sense. But what about the exceptions? What happens when some of these orbital paths actually cross? And this brings us to our final and I think most elegant clue, a hidden cosmic choreography.
The most famous example here is Pluto and Neptune. Pluto's orbit is so eccentric that it literally crosses inside of Neptune's path. Now, based on everything we've talked about, they should be on a collision course. So, why haven't they crashed?
The answer is this beautiful phenomenon called orbital resonance. It works like this. For every 2 times Pluto orbits the sun, Neptune orbits exactly 3 times. This perfect 2-to-3 ratio is like a gravitational lock. It makes sure that whenever Pluto is at its closest point to the sun, inside Neptune's orbit, Neptune is always way off on the other side of the solar system. They are mathematically guaranteed to never be in the same place at the same time. It's an invisible, perfectly natural anti-collision system. It's just incredible.
So, we've gathered all the clues, and it feels like we've cracked the case. The solar system's stability is this amazing mix of physics, history, and pure mathematics. But this leads us to one final nagging question. Is this long, fragile piece we see, is it guaranteed to last forever? So let's just quickly recap our findings. Planets don't collide because 1. They're locked in an endless fall around the sun. 2. They're all traveling on the same flat, one-way cosmic highway. 3. They are the battle-hardened survivors that have already cleared out all their competition. And 4, some of them are protected by an elegant, hidden mathematical dance. So the mystery is solved, right? Well, the truth is, while our system is stable now, it's not perfectly predictable. And that's because of something called the n-body problem. See, calculating the gravitational interactions between just 3 bodies is already insanely complex. But with 8 planets and countless other objects all pulling on each other, the system becomes fundamentally chaotic over really, really long timescales. And this isn't just a theory. Computer simulations have actually shown there's about a 1% chance that Jupiter's constant gravitational nudges could destabilize Mercury's orbit over the next few billion years. And if that happens, it could send Mercury crashing into Venus, or the Sun, or even Earth. So it seems this piece we have might just have an expiration date. So what we're looking at isn't some perfect clockwork machine. It's a dynamic, evolving dance that has achieved a temporary, beautiful state of balance. It's a survivor. And that really makes you wonder, doesn't it? As we look out into the galaxy, how many other systems just didn't make it? And what other incredible cosmic dances, both perfectly stable and secretly doomed, are still out there, just waiting to be discovered?